presentation. For invited speaker, he will have 30 minutes for presenting and answering questions. For regular oral speaker, we have 17 minutes. So please keep the time. Yeah. First speaker is Guido Waldhoff from University of Cologne, Germany.
About the analysis of multi-temporal and multi-sensory remote sensing data with the aim to map crop rotations. The outline of my talk will be, first I want to give a short introduction, then I will present the data and the methods I used, then I will present the results, the discussion and the conclusion, and I will end with an outlook. The study is integrated into the Trans-Regional Research Center 32, short TR32, patterns in soil vegetation in atmosphere systems. That's an interdisciplinary research project with many research areas involved, from geophysics, landscape ecology to mathematics, and the TR32 works on exchange processes that act between soil vegetation and the atmosphere, and the overall goal is to develop new or better models for the prediction of metafluxes in the SVA system. The study area of the TR32 is the Ruhr catchment. This is mainly situated in Western Germany, but also covers parts of the Netherlands and Belgium. And the study area can be roughly differentiated into a northern part that is characterized by rather flat terrain and intensive arable land use, while the southern part is all the low mountain ranges of the Eifel, how the region is called, and the dominant land cover is forest and grassland. Also, there are 3 intensive measuring sites in the study area, which represent the dominant land use types. For the modeling purposes in the TR32 to model the metafluxes, several data sets are important as input data, and that's weather, climate data, soil data, elevation data, hydrology, and of course up-to-date and detailed land use data is very important for the assessment of the impact of the changing land cover on the metafluxes. In this regard, there are several land use products available from official sources. They differ in spatial resolution and quality, and the most of you might know the classical land use data set of the Korean land cover. That's one type of data set, and the other data types that are becoming more and more available for many countries are digital landscape models, which are usually provided by state survey mapping agencies, and also also these data sets contain valuable land use information. Concerning agroecosystem modeling, like it is conducted in the TR32, especially concerning agricultural land use, the information content is rather poor, and because arable land is represented very generalized, so there's no more differentiation. So usually agricultural land is only differentiated into arable land, pasture, specialized crops. And here you can see it in the subset. The scale bar is 1 kilometer, and concerning the arable land, there's not much information there. Often also the spatial resolution is too low, and due to update cycles of more than 3 years, there's no annual data available. So the goal of the study was to provide disaggregated multi-annual land use data, which includes the major crop types and also crop rotations. But also this data should include enhanced information for non-agricultural land use classes. So in this study, has the goal to produce a crop rotation map for the years 2008 to 2010. But in this presentation, I will focus on the production of the annual land use of 2008. The general idea for the production of enhanced land use data was, on the one hand, to use multi-temporal remote sensing data to retrieve annual vegetation and crop type information from optical multispectral data, and to combine this with GIS methods for the integration of additional data that's available and also contains valuable information. And also just GIS methods will be used for the crop rotation mapping. So with the combination or the integration of different data sets, the goal is to enhance the information content of land use data sets. And for this goal, the multi-data approach was used. That's the kind of old approach which has its roots in the late 1990s. And it's like I said, it's a combination of GIS and remote sensing methods. There is a remote sensing part first, and then the second part is the GIS part, where various data sets are integrated, and this is done with a multi-layer raster file, and by using expert knowledge-based production rules, the information of the various data sets is integrated into the multi-data approach land use as the final data set, and also the expert knowledge-based production rules are used for the crop rotation mapping. Like I said, there's also, besides the remote sensing data, there's also additional data available that contains important information. And the first data set we integrated was the Authoritative Topographic Hydrographic Information System called ATGIS. That's the digital landscape model for Germany. That is provided in vector data, although on the image it's already rasterized. And this data set is known to have a very high spatial accuracy because it's coming from survey and mapping. The information content is topographic information like places, road network, prominent landscape features, but it also contains valuable information concerning residential and industrial land use, or even concerning agricultural land use. But as you can see, also in this data set, the arable land is not much differentiated. The second data set we use for the analysis is called physical blocks. That's in German Feldblöcke. And these are, this is vector data, polygons that represent areas of arable land, pasture, or permanent crops. And but it's not single parcels, land parcels. It's the definition of a physical block is that covariant parcels of the same principal land use type, like arable land or like pasture, are put together, and they are bordered by a persistent enclosing, like the road network or a river, or is bordered by forests. And so it's not single parcels, but it covers for Germany the entire agricultural area, and also it should be available in maybe a little different form also for the whole European Union. And the great thing about it is that it's annually updated. So concerning the remote sensing analysis for the crop type mapping, you have to think about that the study area is in the temperate latitudes, and due to different crop type phenology, depending on the type and the region, you have to plan about 3 to 5 observation dates during each growing season, so that you can capture all the major occurring crops. And for the crop rotation mapping, you have to have at least 3 consecutive years, because that's the crop rotations are, or the most crop rotations are 3 years or more. And what you need for the remote sensing analysis is good ground truth or ground reference data, and therefore 3 to 4 mapping campaigns were conducted during each growing season in different regions of the study area to account for the heterogeneity of the vegetation cover in the study area. And concerning crop rotations, it was tried to revisit parcels every year, so as much as it was possible. So, because if you revisit parcels, then you also have some kind of reference crop rotation. And also we used aerial photographs for the derivation of ground reference data, which was also available for the study area. And this training and these ground reference data sets were either used, or some of the data was used for training of the classifier, and other data was used for the post-classification validation. So the remote sensing data we've chosen for the analysis comes from ASTER, from Landsat TM and ETM+. Also, we incorporated IRS P6 from 2009 on, we also could include rapid eye data in the analysis. And for 2008, we selected 4 scenes for the analysis, and the first one is from the beginning of May of Asta. The second one is from the 10th of June from ISPRS 6. The third scene we use is from L7 from the mid of July. And the fourth scene is from L5 of September, 9th September. The pre-processing of the remote sensing data included data-specific processing steps like radiometric calibration, geometric correction. Scenes had to be mosaiced, or we had to subset them. Also, in case of the L7 data, we had to apply a gap filling because of the malfunctioning of the scanline corrector of Landsat ETM+. And for this study, it was decided to resample all data sets to common spatial resolution of 50 meters. And we chose this resolution because it's a trade-off between the capabilities of the sensors in terms of spatial resolution, and this resolution still allows the capturing of single agricultural parcels. And just to mention it, we did no atmospheric correction because we derived the training data from the remote sensing data itself, so it wasn't necessary in our opinion. So for the multi-data approach, we had to conduct some data preparation, and the first thing was that we had to rasterize the vector data, which was selected to be included in the analysis. So we chose some layers of the ATKIS, and we rasterized the physical blocks also to a cell size of 50 meter, just like the remote sensing data. And what's very crucial about multi-temporal and multi-sensor or multi-data analysis is that every data set has to, or all data sets have to, spatially fit perfect together. And therefore, as a base layer for the co-registration of all data, we chose the roadmap network of the ATKIS because it's known to have a very high spatial accuracy, and it's also the ATKIS is also the base data set for a couple of other official data sets in Germany. So they should all then fit together. And to assure that the layers fit together very good, we also used the rasterized version of the ROSE network as a snap raster, so that all the data sets are aligned to each other. Concerning the remote sensing classification, this study of 2008 also should give some answers about what is the appropriate classification method for this study. And therefore we chose, on the one hand, support vector machines, which are frequently used at the moment and are like state of the art. And on the other hand, the maximum likelihood classifier, which is used in remote sensing for decades, and we wanted to find out how competitive they are. So therefore, we classified all remote sensing data sets with both algorithms, and we also used the same training data sets for both classifiers. And then, concerning the general land use mapping, we classified the entire scenes, and for the crop mapping, we used the physical block data as a kind of a mask so that we're able to only classify the arable land. Then for the GIS analysis, after the classification was finished and all data conversion was conducted, these all data sets were combined into a raster layer stack. And from this data set, or on this data set, we applied expert knowledge-based production rules. On one hand, to transfer the information of the remote sensing observations, especially the crop information or the vegetation information, and also we took the valuable information of the additional data. And and then all the valuable information is then combined into a new multi-data approach land use layer in this layer stack. And also by the means of expert knowledge-based production rules, the crop rotation was derived within this raster layer stack. So then I come to the results, and this table shows the classification results of the classifiers for entire scenes, and what you can see is that both classifiers produced comparable results, and that's also this you can also see for the physical blocks of the classification. And we also use the same validation data for both classifiers, and some might think that the accuracy values are kind of high, but that was not the main reason we want to show this accuracy results. The main reason was to show that that both classifiers produced comparable results. Most of the time, support vector machine was a little bit better, but sometimes even the maximum likelihood classifier produced higher values. So more or less, we have comparable results, and for this analysis, the relative difference of the results is the important thing about this. And concerning the multi-data land use for 2008, that's the whole classification image, and here's a subset of it. And the data set includes mainly the arable land and forest classes these classes stem from the remote sensing analysis, and especially for depending on the themes that were incorporated, especially the ASTA and the ISPRS theme were used for the differentiation of winter wheat, winter barley, and rapeseed. And what is important about this is that at this time in the growing season, parcels that potentially contain root crops or maize are bare soil. And for the later analysis, this is a very important fact. Because then with the third scene from L7, mid of June, then we could use the information of the first two observations and then differentiate potatoes and spring barley. And with the last scene from L7, we also could detect maize and sugar beet. Concerning land use classes that were refined using the additional data of APKIS and the physical blocks, could use them to differentiate this data to differentiate urban from agricultural vegetation. Also the pasture information that is included in the physical blocks was incorporated. We used the road network and integrated it into the land use classification. And also we could differentiate residential land use from business land use. Now I come to conclusion. So the first conclusion is about the classification algorithm. The accuracy assessments showed that more or less both classifiers produced the same results. Most of the time the support vector machine was a little bit better, so there was more homogeneous objects or less salt and pepper effect, but the support vector machine needed significantly more processing time in terms of few minutes to a couple of hours. So if you then relate this, the processing time and the results that you can achieve with the classifier, then we came to the opinion that the maximum likelihood classifier still is very competitive, even compared to support vector machines. And yeah, that's why we thought that the choice of the algorithm was less important for our study, and more important was that adequate remote sensing data and training data is available for the intelligence. Concerning the remote sensing analysis, the differentiation of crops was possible with multispectral data, but only through multiple observations at certain stages in the growing season were available, because only in rather short observations, short time windows, you can, for example, differentiate winter wheat from winter barley. And to achieve a sufficient temporal and spatial coverage of the study area, it was absolutely necessary to include multiple sensors. So with one optical sensor, this is kind of hard to achieve. And so we even had to include the defective L7 data, but it was useful for the study, even because of due to the data gaps. Concerning the integration of multiple data sets, we think that we can significantly enhance the accurateness and the information content of land use data with the multi-data approach compared to standard remote sensing analysis alone. For example, the road network was very important for the co-registration of the multiple data sets, and with the incorporation of the physical blocks, what you usually often have is misclassification of agricultural and non-agricultural land use, and for example the pasture and cereals, and by the integration of this data set, this problem is mainly solved, because we have the pasture information from the physical blocks. And also by integrating other data set, other information layers from ATKIS. You can also integrate information in a land use data set that is very hard to detect by remote sensing alone. So, as an outlook, the next steps will be to integrate even more data in this approach, like nature reserves, biotopes, water protection areas, because and management data, like days of storing, fertilization, and so on, because concerning agriculture, agro-ecosystem modeling, these information or these facts have great input or impact on modeling results, because, for example, fertilizer application in a water protection area is limited compared to a normal agricultural parcel, which is located in a non-protected area. And the second outlook is the crop rotation map. So what you see here is a kind of prototype of the crop rotation map, and each color represents unique crop rotation. This was also produced by incorporating land use data sets from 3 years by using, and the analysis was done also with the multi-data approach. With this data set, we will then be able also to model the future land use, because we now have the crop rotations. And the first results are that usually there are recommendations for crop rotations. For example, in this study area, or in this area, there is a crop rotation, root crops, winter wheat, winter barley, and as you can see, it's not that much often practiced like it's recommended, and even crop rotations like with, for example, winter wheat in 2 years after another, which is not recommended, but it's very often practiced. So and the crop rotation maps gives several information concerning which crop rotations are practiced, and in what frequency and in what spatial in what spatial distribution. Okay, so that's the end of my talk, and thank you for your attention. We classified each classification for itself, and then we put them together in a layer stack, and then we used with the production rules we generated, you can transfer the specific information from one layer to the other. So if we want to keep it simple. We said, okay, select all pixels that are land use type X and transfer it to the final layer. And this is what we did for all data sets.
Thank you.
Any other questions?
Hi, thanks you're presenting. And I have two questions I want to ask. And the first point, I'm very curious about your input may allow the variable that you be choose according the remote sensing data or the soil map data. And did you ever do the standardization before? I would want to know, ask that about. And the second point, and could you go back to your PowerPoint slide 21? And I see you only use the training data point and to show ours your model accuracy. And as I know, if we want to check the model performance, we will use the pre-sample validation. One partial for model training, one partial for model validation. We need a test data set for model validation. So you show the different model use a non-parametric SVM model and the MLC the model. They seem like they do not have significant difference as I see, because according to my viewpoint, I think SVM were much better than MLC and significance. So that's my comment, and I want to ask the 2 points in question. Thanks.
I'm sorry, I think I didn't understand your. So what was the first question?
Okay, a brief state. Okay, sure. And did you do your variable have the standardization before? Variable, your predictors, did you deal the standardization? I mean, you use the different variables, right? And have tried to do before standardization. Because they have the range from 0 to high value, and the different value, you need to make a scaling. So I want to know about you have to do this. And the second point, you should only show the training data resource. That means you ever try to use the test the data. You split your total number sample, and one partial for model development, and one partial for model validation. Yes, so you have to make the test data result. I want to ask this about this.
So what do you mean with the test data result? So we used some part of the reference data we collected for the training of each classifier.
Yes.
And for the validation, we used other reference data we collected.
Yes. Because if we want to know about the consistency or the robust the result, we need to use the test data result and to show everyone your model is a good performance, and we can use and to try in the validation.
So no.
Okay.
If I understand you correct, then we did no standardization. But since all data sets came from the same pool,